Welcome to the video for lesson 1.4, Finding Limits by Analytic Methods. Here we get to finally get into more algebra, which might be exciting to some of you. So ultimately in this lesson, we are looking to evaluate limits or finding limits using analytic methods. So more algebraic manipulation and other things. So if you only observe the graph of a function, it can be misleading when finding the limit of a function. In this lesson, we're going to explore how to find limits using algebraic techniques and other limit theorems. So some of our methods to analyze, these 6 steps is really what we're going to, kind of our checklist, right? We're going to start with what's called direct substitution. Then we're going to use other basic limit theorems if possible. Factor and cancel technique would be one to use, and then go back to step 1 after that. Something called the conjugate method, used with rational functions, and then other special trig limits. Another one that we can use is called L'Hopital's rule. We won't see that until unit 3. Okay. So the substitution theorem. Okay, this is really the direct substitution. If our function is a polynomial or a rational function, then the limit as x approaches c of some f of x should equal f of c. And that's simply because the polynomial function exists everywhere, and the rational functions, and here's that provided piece, provided that if the function is rational, then the value of the denominator does not equal 0. So if we can truly evaluate the function at the target value c, then we just plug it in and evaluate. So let's see what direct substitution looks like. So part A of example 1. Okay, we want to find the limit of this quadratic function as x approaches 2. That means we can simply plug in 2 and evaluate the function. Okay. So we do that, work through that calculation, evaluate that. We should get 6. So our limit as x approaches 2 of this quadratic would be 6. Part B, if you need to see another example, even though this one's rational, we can still plug in the 2. 2 to the third plus 1 over 2 plus 1. We notice our denominator is not going to be 0, so that's a good sign. Our numerator is 9, so our limit would be 3. Okay, so always try direct substitution first. If you get 0 divided by 0, or infinity over infinity, or division of 0, these are called indeterminate forms. The goal would be to simplify using other techniques, which we'll learn as we see some more examples in this video. Okay, so a few more examples. Getting into some natural log functions, and trig functions, just good things to review. If I directly substitute my e in for x, we're going to get the natural log of e over 3e. Okay. The natural log of e is just 1 and 3e. So 1 over 3e would be our limit. Part D, directly substitute your 4. Be the cube root of 8, which we know is 2. A trig example, the limit as theta approaches pi over 6 of sine of 2 theta. So we want to evaluate at 2 times pi over 6, which is the same as pi over 3. Think about your unit circle from last year. If you don't remember that, then at least remember this, right? Pi over 3 represents a 60-degree angle. So if you want to draw a triangle that has a 60-degree angle, okay, there's my right angle, opposite the 30. If I use my 30, 60, 90 rule, so it would be the side that's 1 unit. Opposite the 60 would be square root of 3 units, and the hypotenuse would be 2. The sine is the opposite divided by the hypotenuse. So opposite of the 60-degree angle would be the square root of 3, and the hypotenuse is 2. So square root of 3 over 2. Otherwise, you have your unit circle memorized. And finally, the limit of log base 3 of x plus 4 as x approaches 5. Just remembering how to evaluate log expressions. This would be log base 3 of 9. And if we're trying to evaluate that, remember we're thinking 3 to what power is 9 to answer this question? And that's really 2. Okay, so what might happen, and I'll come back to this question here in just a second. We're going to look at our next example. Just consider this limit at the bottom before you read the rest of it. Excuse me. If we tried to directly substitute this x value of 2 in to evaluate the following limit, something interesting happens. Right, if I plug in a 2, we get 4 plus 2, which is 6. 6 minus 6, we get 0. We get 4 minus 12 plus 8. We also get 0. Right? We have an issue. We can't take 0 divided by 0. We can't even take, let's say this was 8 in the numerator. We can't take 8 and divide by 0. So we're getting an instance where direct substitution does not work. Okay? And so we need to use other methods. Okay? So we'll see that in just a second. So I go back to the top. Well, discontinuities, places where functions fail to exist. What's the process for finding these discontinuities? This is a little bit of review. Might be a little far away from you in terms of remembering this. Okay. But how do we find discontinuities? Well, we factor. We factor the numerator and the denominator and simplify. Usually, or oftentimes, you're going to see some of those factors cancel out, allowing us to simplify the function. And that's really where we might see some holes in that rational function. So then remember that a point discontinuity which we talked a lot about in lesson 1.2, occurs when factors are removed. When they're canceled out. And so then that point discontinuity occurs when that factor of x minus a equals 0. And we really call point discontinuities like this removable, okay, because they are canceled out or removed as we simplify, as we factor and cancel. So then a non-removable discontinuity occurs if factors don't cancel and in the denominator when x minus a equals 0. When I'm been talking about with numbers 2 and 3 especially, we need to do some more review on, and we will so as we continue to work more and more with rational functions and evaluating limits. Okay, so don't get too hung up on something in there if it's not quite making sense. It's an ongoing process as we continue to learn about this. Okay, so you can perform the same algebraic analysis that we have done previously in our study of rational functions to find the limit of removable or point discontinuities and non-removable, or what we would also call infinite discontinuities, using the factoring method or cancel technique. So let's use this on this limit that so far, using direct substitution, we can evaluate. Okay, so this whole factor cancel. This limit, as x approaches 2, this function, I should say, can be simplified by factoring the numerator and the denominator. Factors of -6 that add to 1 would be positive 3 and 2, x plus 3 and x minus 2. Bottom, factors of 8 that add to -6, that has to be -4 and -2. We can see I have a pair of factors that are going to cancel. X minus 2 divided by x minus 2 is 1. So a reminder that this tells me that there must be a whole where x minus 2 equals 0 or at x equals 2. Okay, so we call that a removable discontinuity because that factor was removed. Okay, so now our limit has changed as we simplify this. And so if I try to use direct substitution now, I'm just going to go d dot s for direct substitution. Okay, plug in my 2. I notice I no longer have division of 0. I no longer have that indeterminate form. We get 5 over -2 or -2.5. Okay, so this is the factor cancel method. So far, check direct substitution first if that doesn't work and you're working with a rational function. Factor and cancel. Okay. And then we'll continue with some other methods as well. I want to pick apart this function a little bit more as we continue talking about other analytic methods of evaluating limits. So graphically, let's just connect to that analytic version versus graphically. Okay, just where we really wanted to make sure we were today. So graphically, looking at the function, we can see that just because it is undefined at a specific x value doesn't mean that we can't find the limit. So let's use the graph to determine the values of each of the limits below. Notice we're given the location of the whole as well at 2, -5/2. So the limit of this function, which we just worked with as well, as x approaches 2, we found that already analytically, that was -5/2. But if we look at an x value of 2, we can see the location of that whole, right? It canceled out, and so we have that point discontinuity, that removable discontinuity here. And so that y value was -5/2. Okay, graphically, evaluating the limit as x approaches 4 from the right. So our asymptote. From the right side, we're approaching positive infinity. And from the left side, negative infinity. Right, we already discussed that. If you consider what happens when you try to evaluate the limit using direct substitution with any of these, right, it leads to 0 over 0. It leads to indeterminate form. So remember, if you get indeterminate form, your goal is to algebraically manipulate the expression in effort to remove those points or there's more than one, of discontinuity. Then try direct substitution. Okay, so what about one-sided limits then, right? Because we had a couple of those above. How would you use direct substitution to evaluate a one-sided limit? Okay, so if we were to analytically evaluate this one, how do we do so, right? Well, we already know that above, this should be infinity. Okay, graphically, we know that this limit should be positive infinity. Okay, how could we show that? So as x approaches 4 from the right, what we're going to do is we're going to pick a value to the right of 4. I'm not talking about 5 or 6 or 7, right? I'm talking directly to the right. Then analyze the simplified function. Okay, so what if we use, right, and we're going to make sure we do this. We know that this limit does in fact equal our simplified version, which was x plus 3 over x minus 4. So if we use the simplified version, I'm going to do this instead, I'm all messy. So if we pick x to be like 4.1, okay? I could do 4.1 plus 3 over 4.1 minus 4. Okay, well I'm going to get 7.1 and I'm going to divide by 0.1. Okay, obviously we know if I even go punch it into the calculator right now, what did I just do? There we go. If I punch that into the calculator right now, we're going to get an actual value, right? 71. Okay, well what if I picked 4.01? Okay, what if I picked a smaller value? We're going to get 7.01, but we're going to divide by 0.01. I got an even larger value. What if I picked 4.0001? An even larger value, right? So as I continue to get closer and closer to 4 from the right, this really is going to be a very large positive number. It really is going to be infinity. So as we approach 4 from the right, as we get closer and closer, right? That's what you saw me doing in the calculator there. What if we were 1/10 away, 100th away, 1,000th away from 4 on the right-hand side? Our function keeps getting larger and larger, and infinitely so. So as x approaches this value, y approaches infinity. So our limit is infinite, and there's our proof. Okay. So again, evaluating left and right-hand limits, you can actually pick values and sort of test them and use direct substitution in your simplified function to analyze it. Okay. So if we see it one more time, let's pick a value really close to 4, but this time from the left. So like 3.999. Okay. So if I plug that into my simplified version, my numerator, I was adding 3. And then the denominator, it was that x value minus 4. So I'm getting 6.999 over negative 0.001. Again, if you need it, the calculator, go ahead and I got the right number of zeros there. Yep. Go ahead and divide it. We see we get a really large negative number. And if I made that even more so, closer to 4, if I said my x value was 3.9999, right? 5 nines. Okay, my numerator would be 6 and then 5 nines. My denominator would be negative 0.4001. An even larger y value, right? So we can see that this is really going to go towards negative infinity. Okay, again, we'll do more with direct substitution and more evaluating of left and right hand limits analytically. Just a little touch on it now. Okay, so a few more methods. Piecewise functions. How do we evaluate limits with piecewise functions? Okay, we want to evaluate the limit as x approaches 1 on our g of x, given g of x as this piecewise function. Okay. Remember, in order for this general limit to exist, we need to analyze the limits from both the left and the right. That's what I'm getting ready for. In a piecewise function, you are given the left and the right-hand sides of the function. Okay? The right-hand side of the function is going to be where x is greater than 1. The left-hand side of the function is going to be where x is less than 1. So if we plug in and directly substitute, in this limit, we're going to use that. I'm actually going to write it like this. The right-hand side of my limit is that x cubed plus 1. And so if I directly substitute my 1 in, we get 2. Okay, the left-hand limit would be the left-hand side of the piecewise function, the x plus 1. And directly substituting a 1 in, we get 2. Because these are the same, we just prove that the limit as x approaches 1 from the right is equal to the limit on the left. Therefore, our limit, our general limit as x approaches 1 on this function has to be that value of 2. Okay. You could try part B on your own to be proper about your argument. You would want to follow the same steps as part A. So show your right hand, show your left hand, show either they're the same or different, and provide your answer. Okay. If I just tell you the answer to part B, you can process through it on your own. This general limit should be 3. Okay. So a little bit more practice in selecting different procedures for determining limits. We're just going to work through some examples. And actually, I'm realizing that example A is the same as previous example. I need to fix that. So we'll skip that one. Okay, well, part B would be a good one to take a look at, the factor cancel technique. Seeing that again. Okay, this is a bit of a doozy of a rational function to factor, so good review here. First, check direct substitution, right? So first, check direct substitution. If we plug a 2 in, 2 cubed is 8, minus 2 times 4, so minus 8, plus 10 minus 10, our numerator, we get 0. Denominator, we're getting 8 plus 8 minus 26 plus 10. Let's see, 8 plus 8 is 16, minus 26 would be negative 10 plus 10 would be 0. So we get our 0 over 0, direct substitution didn't work. So now we resort to the factor cancel. So let's factor and cancel this puppy. So this thing we can group. We can factor by grouping both the numerator and the denominator. So my first pair in the numerator, I can factor out an x squared to get x minus 2. And I can factor a positive 5 from the second group to get x minus 2. I get that common factor, so I know I'm on the right track. The denominator, oh, this is a tough one. We're going to come back to the denominator for a second, because if I try to factor by grouping on this one, I'm going to take out that x squared and get x plus 2. But there is no common factor in the second group, negative 13x plus 10, so we can't factor this one. We'll use it with this method, we'll use a different way to do that, which is a good thing to review as well. So we know our numerator can factor into x minus 2 and x squared plus 5. So then how do we factor the denominator? Well, we don't factor, we divide. Okay, we use our heads. If the numerator has a factor of x minus 2 or x squared plus 5, there's a good chance the denominator shares one of those factors. So we're just going to use long division to try to factor the denominator. I'm going to start with the x minus 2 and just hope that that was a lucky guess. So can I take that, I'm going to show my work down here. Can I take that denominator and use polynomial long division to divide it by x minus 2? Okay. So remember, we take first terms in each one, so I'm trying to figure out how many times does x go into x to the third power. It goes in x to the second times. Distribute that out. X squared times x would be x to the third. X squared times negative 2 would be negative 2x squared. And then I subtract. 1 minus 1 is 0. 2 minus negative 2 would be positive 4. Bring down your next term, negative 13x, and start over. How many times does x go into 4x squared? This time it goes in positive 4x times. Distribute that back out. 4x times x is 4x squared. 4x times negative 2 is negative 8x. Subtract. 4 minus 4 is 0. Negative 13 minus negative 8. We get really plus 8, so negative 5x. Bring down the final term. Start over. How many times does x go into negative 5x? It goes in negative 5 times. This is my last round, so if this x minus 2 is truly a factor of that denominator, I should get a remainder of 0. So that's what we're hoping for. Let's check. Negative 5 times x is negative 5x. Negative 5 times negative 2 is positive 10. Subtract. Negative 5 minus a negative 5 is 0. 10 minus 10 is 0. Perfect. So that tells me x minus 2 is a factor of the denominator, and the other factor is this x squared plus 4x minus 5. Okay, so these cancel out. So we know that there's a hole at at x equals 2, a removable point discontinuity. But our new limit we can write and look at the limit as x approaches 2, x squared plus 5 over x squared plus 4x minus 5. So let's try direct substitution now. 2 squared would be 4 plus 5. 2 squared plus 4 times 2, so 4 plus 8. 12 minus 5. So we're getting 9 over 7. It worked. Okay. Another method we can use to evaluate limits analytically is the LCM method for complex fractions. This is quite an interesting one with the algebra. Use this anytime you have division of another fractional, sum of fractions at that, okay? So when we look at what's in the denominator, 1/4 plus 1 over x minus 4, we're going to look at the lowest common multiple of those denominators. And so that LCM is really going to be those two denominators multiplied. Okay. So we want to multiply the numerator and denominator by that LCM. Here's what it looks like. Take the original expression. Okay. We want to multiply that by our LCM, both numerator and denominator. So we're going to get 4x, and I'm going to leave it like that for now, times x minus 4. Keep my limit notation with me. When I take 1/4 and multiply by 4 times the quantity x minus 4, I'm just going to jot it out to the side. Some of you might need the visual. If I'm multiplying these two pieces together, my 4's are going to cancel. That's the whole point of this. So really it becomes 1 times x minus 4, or x minus 4. And then we have our plus sign still from the original. Then if I take the second fraction and multiply by that, so I'm just going to change these out. Show the visual. This time the x minus 4's cancel, and we get 1 times 4, or just 4. So we see that by multiplying by the lowest common multiple of those denominators allows us to cancel out the fractions with the complex fraction expression. Okay, so we can simplify this a little bit. Negative 4 plus 4 is 0, so those cancel. X over x would be 1, so this is really the limit as x approaches 0 of 4 times x minus 4. If we use direct substitution, we're getting 4 times negative 4, or negative 16. Okay, show you a second example of that one. Similar to it. Again, this could be a good one if you just want to pause the video and try it. If I look at my denominators in the complex fractions, my LCM is going to be 2 plus x times 2. And so we're going to multiply that by both the numerator and the denominator of this function. Multiply your LCM to both. I start with the denominator. Simplify x times the quantity 2 plus x times 2. That's just going to be 2x times the quantity 2 plus x. Feel free to simplify that more if you'd rather. I like leaving it separate until we get towards the end. Then if I multiply those over, we're going to get those denominators to cancel. So 1 over 2 plus x times 2 plus x times 2. The 2 plus x's are going to cancel out. So we just have 1 times 2, or 2. 1/2 times this. This time the 2's are going to cancel. So we're going to get 1 times 2 plus x. But keep in mind we do have that subtraction symbol going on. And so we're going to have 2 plus x in parentheses. Simplify. 2 minus 2 is 0. But then we're going to have negative x because of that distribution of the negative. What I have left in my denominator. The x's are going to cancel. So we have the limit as x approaches 0 of negative 1 over 2 times the quantity 2 plus x. Go ahead and directly substitute now. This is going to be negative 1/4. Okay, the last technique in this pretty long lesson here is the rationalizing technique, or what we would call the conjugate method. We would use this with radical functions, radical rational functions, I should say. So the graph of our radical rational function is provided at the right. Okay, so we can use that graph to just kind of solidify our understanding as we move forward. Conjugates. Okay, we use conjugates to cancel out radicals. Okay, if we try direct substitution with this, we're going to get 0 in the denominator. Right? If I plug in a -1, -1 plus 1 is 0. So we can automatically see that direct substitution is not going to work. So instead, if I multiply this expression by the conjugate of that numerator, that radical function. So if I take and multiply by the square root of x plus 2 plus 1, both numerator and denominator, we can get the radical to cancel out and some other interesting algebraic things to happen as we simplify it. Here we go. Square root of x plus 2, I have to distribute the numerator. Square root of x plus 2 times the square root of x plus 2 is going to be just x plus 2. Okay, if I take the square root of x plus 2 times 1, I'm just going to show it, you're going to get square root of x plus 2. If I take negative 1 times the square root of x plus 2, we get negative square root of x plus 2. And hopefully you realize right away that both of those will cancel out. That's why we write conjugates. So then the square root of, negative 1 times positive 1, we get negative 1. Our denominator, I'm going to go ahead and leave those separate for now. So we have this x plus 1 being multiplied by the square root of x plus 2 plus 1. Okay. In my numerator, this x plus 2 minus 1 reduces to x plus 1. So x plus 2 minus 1 is going to cancel out with x plus 1. So now my new limit, as x approaches negative 1, my numerator now has nothing up there except for a 1. My denominator says the square root of x plus 2 plus 1. And if I directly substitute this now, we get 1 over the square root of 1 plus 1, which is 2. You can see with the graphical piece how that makes sense. The limit as x approaches negative 1 is 1/2. That y value. Okay, let's try that another time. Right away, I recognize that if I plug in a 5, number 1, if I plug in a 5, we're going to get 3 minus the square root of 9, which is 0. But I also notice that there's a square root in here. And so we should just, that should be an indicator right away. Okay, let's use the conjugate method. So the conjugate of that radical chunk of the function would be 3 plus the square root of x plus 4. Multiply that both numerator and denominator. Work through your algebra. Keep in your numerator, nothing's going to cancel out because they're not conjugates. So my rule of thumb is just keep it separate. Don't expand any algebra unless you have to. Okay, that's actually something to kind of start talking about with the AP test as well. On free response questions, you're not required to simplify anything. And so you could leave it just like this so far. The denominator, however, because they're conjugates, I don't have to distribute or multiply all 4 of those quantities out. I know 2 of them are going to cancel like we saw above. So I can just do 3 times 3, which is 9, and negative square root of x plus 4 times positive square root of x plus 4. That's going to be a negative x plus 4. Okay. If I simplify what's in the bottom, I'm actually going to write this one out. Otherwise, I think some of you will miss this very minimal thing. It happens on this one algebraically. 9 minus x minus 4. Right? If we combine some like terms, or if I even just rewrite it underneath, this really says 9 minus x minus 4. So if I rearrange 9 minus 4 would be 5, positive 5, but then I have a negative x. And if we look at our 2 factors, we see that those are exactly opposite. So these two actually cancel to -1. So now our new limit says -1 times a quantity 3 plus the square root of x plus 4. And let's turn to direct substitution. -1 times a quantity 3 plus the square root of 9, which would be 6 times -1 over -6. Okay, last little bit of the video is just trying to kind of put it all together. Okay, this would be a great chance for you to pause the video and try each of the examples to figure out what method should you use and how should you go about it. I am going to continue the video explaining each one separately. And this video will end with these 4 examples. You will see a second video that talks specifically about the squeeze theorem for this lesson. So again, pause the video if you want to try these. Otherwise, here we go. First thing I recognize about the limit in part A is that it's polynomial. I should be able to use direct substitution on this one. I'm just going to write that, direct substitution, d.s. So if I plug in a -2 and evaluate, we can figure out what our limit is. We get -8 plus 12 plus 8 plus 5. This should be 17. Part B, I right away notice 2 things. It's a rational function, so perhaps I can do some factoring and canceling, but I also notice it's a right-hand limit. So, go ahead and try to factor cancel first. This would be our AC method. Let's see, I've got to start with a 3x and an x. It's got to be a 2 and a 1 to get -7. So the 2 must go here to help us get 6x, and then there's our 7x. So let's get our signs right, because it's negative in the middle, they both will be negative. Okay, in the denominator, we have a difference of 2 perfect squares, so we have an x plus 2 and an x minus 2. So those cancel. Okay. And so now we're looking at from the right of our new limit. So we can use what we've done in the past, picking a value that's close to 2, but there's actually something on this function that we should talk about as well. If we plug in a 2 to the denominator, even though it's a right-hand limit, if we plug in exactly 2, we're not going to get 0 down there. So we can use direct substitution because it's continuous. At x equals 2. Okay, because if I ignore the fact that it's a right-hand limit, 2, if I plug 2 into the denominator here, 2 plus 2 is 4. I'm not going to get 0. I'm not going to get indeterminate form. So we can just use direct substitution on this one rather than picking, 2.001. This direct substitution is a lot easier. We don't have to pick up our calculator to help us with it. So we get 5/4. Okay. What do you notice when you look at part C right away? It's a complex fraction, so we should use the lowest common multiples to help us evaluate that. That lowest common multiple is just going to be multiplying those 2 denominators. So I'm going to multiply this by x times x plus 3 right away. what I haven't done on the last two problems is I haven't directly talked about how direct substitution is not going to work. Here, hopefully it's pretty obvious. If I plug in a 0 for x, I'm going to get 0 on the bottom there. I can't divide by 0. So direct substitution doesn't work. Turn to other methods. Okay. My new expression, my denominator is going to be x squared times x plus 3. My numerator, those x's will cancel, so I'm going to get x plus 3 plus, I know the x plus 3's are going to cancel, so just plus x. Now we've got 2x plus 3 over x squared times x plus 3. Let's try some direct substitution. I plug in a 0. We're going to get 3 over 0. So this is actually a good thing to talk about. We tried another method, and we still got an undefined value. So this must mean that it doesn't exist. Okay, last one. This looks like a pretty intense one. Looks like kind of maybe intimidating, right? Because we've got h's and things in there. So we just changed our variable. We're looking at the limit of this function as the h approaches 0. So of course, if we plug in 0 for the h's, we're going to get division of 0. So what else could we try? Well, algebraically, I could actually expand all of this out. So x plus h squared would be x squared plus 2xh plus h squared. This would turn into minus 3x minus 3h. And then our minus x squared minus, no, sorry, minus negative, so plus 3x all over h. So I'm not doing anything fancy. I'm just expanding the numerator out. It looks like we can simplify some stuff. I've got a negative 3x and a plus 3x that'll go away. I've got an x squared and a minus 3x that'll go away. So my new limit can say 2xh plus h squared minus 3h all over h. And then I notice all three terms in the numerator have an h, so I can cancel out an h from all of them. Final new limit, 2x plus h minus 3. So if I plug in, directly substitute 0 for h, this is going to be 2x minus 3. This is a snapshot into something in the future that we will discuss more in context as we continue. So finally, pretty long video for this lesson. Lots of content in here that takes time to discuss and time to explain. But this first part of the video, how do we evaluate limits using algebra? Okay. Look for, like I said, part 2 for this lesson that talks specifically about the squeeze theorem, a little extra that we'll discuss here.